because it takes a minute. Okay, thank you everyone for joining us on the last Tuesday for this academic year, for those of you who are on the academic schedule. In the California Fire Science Seminar Series. I am Dr. Crystal Colden at the University of California, Merced. My co-hosts and co-organizers in this series are Dr. Jeanette Cobiana-Niguez from University of California, Merced, and Dr. Michael Gallner from UC Berkeley. We are thrilled that you have joined us all year long, and we're absolutely thrilled to have our guest today, who I'll get to in just a minute. For a few logistical things, if you haven't joined us before, this webinar is such that you are not able as a participant to speak or ask questions verbally or turn on your video during the webinar. It is presentation only. So if you have a question, and we do encourage those, please use the Q&A tool in Zoom, and to locate that, look at the bottom of your screen in the toolbar and look for the little button that says Q&A, and we ask that you please put your questions in the Q&A for our guest to answer. And then at the end of the presentation, we will likely have time for just one or two questions, and then we will move over into a much longer discussion hour. And that actually has a separate Zoom link so that you are able to interact with us and our guest. And the link should have been in the email you received as you registered for this webinar. We will also post that link in the chat box as we get towards the end of the hour here. This seminar series has been in partnership all year with the California Fire Science Consortium. And for those of you who are wondering, because we have had a few folks ask us, the goal is to continue this seminar series next year. We're currently working on the logistics, but it will likely be again with UC Berkeley, UC Merced, and the California Fire Science Seminar Series. So we will definitely be letting the email list know as things get ramped up later on in the summer and as we prepare for fall. But for today, I'm absolutely thrilled to introduce our guest speaker. And that is Joe Scott from Pyrologix in Montana. And Joe is the principal wildfire analyst with Pyrologix. He has been, if you are working in fire and not familiar with Joe's work, then you have not looked at the multitude of products and publications that he has created with colleagues over the years. He's based out of Missoula and has predominantly been focusing on wildfire threat assessment in recent years, and he has led projects related to surface and canopy fuel characteristics. Of course, the Scott and Bergen update to the old Rothermel fuel models, wildfire behavior modeling, crown fire hazard assessment, wildfire risk assessment. Joe conducts wildfire hazard and risk assessments to support land management planning, incident management, and utility wildfire risk management for state and federal agencies and private companies. He has more than 2.5 decades of experience in wildfire behavior modeling research, development, and application. And we're absolutely thrilled to see the new work that he has just been coming out with in California today. So without further ado, I will turn it over to Joe Scott. Thank you so much for joining us, Joe.
You're welcome. Thanks, Crystal, for that introduction. I will go ahead and share my screen. Hopefully get the right one. Part of that, I did not get the right one. Crystal, can you see my PowerPoint again?
Yes.
Okay.
Great.
It's not doing the green bar around it this time. I actually did my very first fire behavior simulation on the Berkeley campus 32 years ago, I think, taking a class where Mark Finney was the TA. It was one of Bob Martin's classes in fire ecology, fire science. Goes way back. So I'm excited to show you all this stuff today. to start off with to acknowledge that I'm here speaking, giving the seminar, but this was a very much a team effort at Pyrologix. Literally everybody at our little company participated. So that's Julie Gilbert-Sinde, our program manager. She was the glue that kept us all together moving forward. Kevin Vogler did all the FSim modeling. April Bruff took the lead on the fuelscape and what we're calling the wildest modeling. Chris Moran did the weather data climatology processing. Jim Napoli worked on the fuelscape to support April, and then Michael Callahan at the end built us some web maps that I'm going to show you at the end of the day today. And then, we've kind of developed this ad hoc working group talking about all lands hazard assessment across California, and that includes our client on this project was the Pacific Southwest region, Patrick Doyle, Randy Striplin, and Kristen Allison. And then CalFIRE's, the FRAP folks, Dave Sapsis, Tadashi Moody, and Jamie Liderson got us the climatology data that we're using and are looking to fund some future work. And then the California State Office of the BLM, James Newman and Eric Kroner, also working with them to support ongoing work in California. So with that, we're gonna dive right in. You all know the state of California. This work was done, like I said, for the Pacific Southwest region of the Forest Service. One thing I'll point out right now is that our analysis area includes a 10-kilometer buffer into the neighboring states. So later on, when you see that little inflection point, when you see it's not in Lake Tahoe, it's not a projection error, that's just the buffer. We completed most of this work late last fall, more or less at the very tail end of the 2020 fire season. But everything I'm going to show you represents conditions as they existed at the beginning of the 2020 fire season, which is great because it gives us a chance to use the 2020 fire season to grade how well our map worked. So to begin with, and this we did a pair of fuel calibration workshops in California at the very beginning of March 2020. And that was really, I think the shutdown started happening a week or two after we got that in, and then we finished the entire project after that. So what we did is started from LANDFIRE Remap vegetation data, which is circa 2016. And then we applied a process that's similar to what LANDFIRE, the fuels team, uses for the remap data, but it's a little bit different. But in general, it's very consistent. The main thing that we did is made one mapping zone across California, whereas the off-the-shelf LANDFIRE has portions of, I think, maybe 4 or so mapping zones, and you can sometimes get seam lines. So we use one mapping zone to eliminate seam lines. Reviewed the rules for the one unified mapping zone with, I think it was 30 or 40 folks up in Sacramento, and then maybe 20, 25 folks down in Southern California in early March. And then we added fuel disturbances that took place after the 2016. So that included 17, 18, and 19. And so what we made is a 2020 fuelscape. So it's for use in 2020. And LANDFIRE Fuels team calls that a 2020 capable fuelscape. So that's what this is all based upon, is a fuelscape that was good before the 2020 fire season. So the main thing that we're going to talk about today with a lot of others is our burn probability modeling across the state. So like I said, we used this 2020 fuelscape, a slightly customized version of the LANDFIRE off the shelf. We used Karen Short's fire occurrence database, which is national in scope, so we use it everywhere we work. The version that we use had data through 2017 in it, so 1992 to 2017. And then we used the gridded historical hourly climatology, 2-kilometer hourly climatology data set that CalFIRE, and I think others, but I think mainly CalFIRE funded the Desert Research Institute to produce, and that was data through 2018. And then we used Mark Finney's FSim model. So Mark's here in Mizzou at the Fire Lab and developed FSim. It's about 10 years ago now, actually. We ran that at 120-meter resolution across the state. I'm can ask Kevin if he's on in the chat later on, if it was 10,000 or 20,000 iterations. I forget which. So 120 meters natively in FSim, and then we upsampled that to 30 meters using the same process that we used for the Wildfire Risk to Communities project. And when we calibrated the FSim model, we used historical occurrence data through 2017, but we used some trends, which I'll show you next, the temporal trends in fire occurrence to project what an occurrence would be for the year 2020. It doesn't have anything, there's no estimate of like what the weather was like in 2020 or anything else like that. So it's using all the information that we used was available for up to a few years before. Okay, and then we looked at historical trends in fire occurrence in 3 different regions across California. This chart here that we're looking at is the occurrence in region in this group 1. It's a group of fire occurrence areas that's basically north of the Bay Area all the way to the Oregon border and then all the way east. It's a pretty large area. And for this analysis here, we just did a very, very, very simple least squares linear regression of, and this chart is total area burned per year. We also did the number of large fires per year, and then by looking at those two together, we get see if there's a trend in the average large fire size. So we used all those 3 of those, but I'm just going to show you the total area burned, which is kind of proportional to burn probability. And that looks like a strong upward trend in area burned, and it is. It's not the strongest in the country, but it's the strongest in California for sure. So that there's the trend line, and here's 2020. So we would kind of have put the overall trend in that area up here at 2020. The dark circle represents the center of that fire occurrence database period. So in the past, that's how we've calibrated, was down to that, not treating this as a temporal sample, but just as if everything were stationary. That's the average way down here. If we only looked at, like, I think it was the year 2000 to 2017, that's the so a more recent time period, that's the blue square. And in every case, what we saw is that all those estimates are very, very close to our trend line, and that gave us confidence in saying that the trend line is not a very bad thing to use at all. Here's group 2. Group 2 was interesting in that, so it's the south coast, and south and central coast, in that it was relatively flat in terms of the overall area burned. It's increasing, but not very quickly. But that came in a very unique way. It came in a downward trend in the numbers of large fires. So the numbers of large fires, large fire here being 100 hectares or 247 acres. A downward trend in the number per year, but a very strong upward trend in the sizes of those large fires that do exceed 100 hectares. And on the balance, those 2 things netted to be a slow increase, slower let up north, and also slower than in the Sierra, this group 3, which was a moderate increase in area burned, and that came from a fairly equal contribution of the numbers and the sizes of fires. And then those groups 4 and 5 are areas that don't have a lot of fire, and they also, partly because of not having much fire, they really didn't have a very strong trend at all. So they're not interesting to look at here. So we took all this information and used a few other tricks in FSim, and this is what we came up with for burn probability. The legend that you see here, and it's going to be a common theme in legends that I'm going to show you later today, is that it's a log-based legend. In this one, every 3rd class is a full common log factor of 10, and the other 2 classes in between are 1/3 logs. So it's a geometric interval. So the red areas are much higher burn probabilities actually than lower down. And one of the things that you'll see here, that there is a burn probability class that's greater than 10%, the 0.1. That's not 0.1%, that's 10% chance per year. Because we calibrated the trend, and the trends in Northern California were so strong, we did find an area with greater than an estimated greater than 10% chance of burning, which we had not seen in the past. And then on the graph here, let me turn on laser pointer. On the graph here shows actual California fire seasons, their results over time. Through 2017 was the last one that we used for our regressions. We did not do a regression through this line. We did the regressions in individual fire occurrence areas and then put them all together. But the larger circle, blue in the center, orange on the outside, that actually represents this map. If we take this map with these individual burn probabilities for their pixels and use it to estimate expected annual area burned in California, we get just a hair under 1 million acres per year. And so I plotted that there. So that's essentially what our individual trends across the state, where it put us, higher than in past years. And as you can see, nowhere near as high as what actually happened in 2020. So 2020 was 4 times higher than that average that we came up with, but our average accounting for the trend, without accounting for the trend, it would have been about 600,000 acres for the state of California. And so accounting for the trend, we went way higher than that, but obviously 2020 was just crazy. But the fires generally burned, there we go, in the expected locations. And I'll show you some more details on this. Is just going back and forth between these. Now you can see that the 2020 fire perimeters and where generally are occurring where BPs are high, which is, you have to burn some areas that aren't high BP. And what we ended up doing not to validate, but really to verify our model, is looked at these proportions. And so first off, this is the land area underneath each one of these burn probability classes. The value on the x-axis here is the upper end of the burn probability range, and that's actually truncated. That's 2.2, that's 4.6, and so on. So basically 10% of California has essentially 0 burn probability. So that's large ag lands, it's water pixels, certain parts of the desert, not all the desert. And then that's 10% of the landscape. And then another, 27% has a burn probability less than 1 in 1,000. So very, very low. And then, so most of the landscape doesn't have much fire. This is going to come into play in a second. And then you can see that, well, there's a fair amount of land cover in all the other BP classes, except for that highest one, the greater than 10%. And actually the highest that we found in there was 13% per year. Almost no land area at all. But on the next slide, this is the expected annual area burned within each one of those classes. So if I go back, no, can't use that. Go back. Most of the land area is in lower BP classes at first, but then most of the area burned, because the probabilities are so high, we should expect to, this is where we should expect to see fire. We should expect to see, between 35 and 40% of the area burned by our map should be in this 0.22 to 0.022, 2.5% to 4.5% chance of burning should be in that really high class. So the question is, what happened in 2020? And there it is. What we did is overlaid the 2020 perimeters onto our burn probability map and summed up. Now, remember, 2020 burned 4.5 times more land area. So I'm not trying to say that our map got the BP right, because I know for a fact it did not. It underestimated by a factor of 4. What we're looking at is it in the right place generally? And this would suggest that it is. It's really, there's an awful lot of luck in this, especially at this the highest BP class had almost no land area, but maybe 1.5, 2% of the area burned should have been in it. But it's such a small target up here in the Klamath area that in any given year you might expect to burn none of it to most of it. But what actually happened in 2020 was it burned almost exactly the right proportion. Now that's just luck. but I'll take it. Okay, so it looks pretty decent. And then here's another way to show that it's looking pretty decent is this is a Lorenz curve. It's just kind of the cumulative form of the previous slide. And so it's the fraction of the landscape from the lowest. So it's the first stuff is not burnable. Then the next 27% is burnable, but it doesn't account for, we didn't expect it from the FSim to account for much area burned. And then we go up from there. And when you look at it like this, it's like, well, that doesn't look too bad. This is way better than we've ever seen before. And I think it's a halfway decent way of judging at least the relative burn probabilities across a large area like this. But of course, as a Lorenz curve, a lot of you might be familiar with that, it's really about distinguishing inequality. And so this is a concept that I've called in the past spatial inequality of wildfire hazard, and wildfire risk is actually, it's even more unequal. So if you look at, if every pixel on the landscape had the same burn probability, the distribution would be on this 1-to-1 line. And the more unequal the distribution is, the more variance, I guess really you'd say, then the bigger this area, the gray area, the area of the gray divided by the area of this rectangle, that's called the Gini coefficient. And in this case, that's 68% essentially. So the Gini coefficient of 68 out of 100. If this were a measure of the inequality of income, it would be the worst, the most unequal in the world. There's no country in the world that has an income inequality higher than 68. I think South Africa is 64. The United States is in the 40s, I think. So California's burn probability is highly unequally distributed across the state. And it's really obviously driven by, you got the Central Valley and then of course the Mojave that has large areas that have very little fire. And we'll do this for other geographies and see if there's other states or other regions of the country that are this unequal. Now, and then I'll look at a couple of other ways to summarize our BP results for California. This is a fire size distribution. It's log scale. If this were a true power law distribution, that would be a straight line. We don't often see perfectly straight lines out of FSim results, but the fact that it comes close to power law at all is pretty impressive, I think. It's really an exceedance probability curve, but when you get to small fires, you get higher than 1, so that's the number of fires. And so what we're seeing here is that 16 fires a year is what our modeling would suggest on average might happen in California. 16 fires greater than 10,000 acres. Yeah, that's right here actually. 16 greater than 10,000 acres, 1.7 greater than 100,000 acres, and the probability of a 1,000,000 acre fire, and this is in FSim, we actually had merged our fires that came together, was 1 in 47 in our event set. So about a 2% chance per year of having an August complex. So the August complex, the largest fire in California, not a single origin. By our modeling, that was a roughly 50-year event. I think the way our modeling works is it's not as good at answering those kind of questions. I would say that probably it was higher than that, maybe 1 in 40 or something like that, instead of 1 in 47, 1 in 50. But it's interesting to see how you can do that. And then, of course, we can do the same thing for a whole fire season. And so this is another exceedance probability curve for area burned in California. And move this out of the way so I can read my notes. The average annual area burned I mentioned earlier was about 1,000,000 acres, 950,000 acres per year. But there's actually only a 35% chance of exceeding that. Yeah, would be right around here. Nope, down here. That's about the average from our BP map. But how do you get that average? Like, well, it's actually only a small chance you're going to have a fire season bigger than that. But if it's bigger, it's a lot bigger. Coming down to the 4.2 million acre fire season from 2020, our modeling suggests that was about a 1% chance. So basically, of our 10 or 20,000 iterations of our simulations, only 1% of them produce that or more. And again, FSim, the way that this stuff was used, it's probably an underestimate because it doesn't really doesn't make what happened in 2020. It doesn't try to simulate that you get all these fires that happen all at once in the same year. And then one other thing that we can look at that was kind of interesting is, you know how we have, well, I just read it in the paper here. The new normals are out, right? The moving 10-year average for climatology is looking back in the last 30 years, and a lot of what they say is like, well, what has a 33% chance of happening being lower than that, 33% chance of being greater, and then there's the stuff in the middle, so divide it into thirds. Well, when you do that off this EP curve, what you can see is that there's actually about a 1/3 chance, so 67% chance that the fire season will be less than 500,000 acres in California, and at the other end, another 1/3 chance that it will be greater than 1 million acres, roughly, right? And then the middle third between 500,000 and 1 million acres is that's not normal, but the normal is that you'd be within those range with those probabilities. And obviously that nothing is stationary. So that was 2020, and 2021 and 2022, those would be slightly different answers. But that kind of puts into context that what happened in 2020 from our modeling was a rare event by a lot, very, very rare, but not unheard of. It was simply on the tail, but at least it wasn't off the tail of the distribution. Okay, so I'm going to transition now to talk about something that we've been calling WildFS for wildfire exposure simulation. So we're using FSim for burn probability, and that was at 120 meters. And then downscaled, but for everything else, we're using the WildFS, which is really just FlamMap, Mark's other tool, but we do it for 216 weather types, so different combinations of wind speed, wind direction, and dead field moisture content. And then we simply weight those back together. So we do 216 runs at 30 meters. We use Wind Ninja for adjusting to the winds to terrain, and we use field moisture conditioning to adjust fine dead field moisture to reflect mostly canopy cover and aspect. And so that shows up in there. And so to do that, this is where we use that gridded hourly 2-kilometer climatology that the DRI produced for CalFIRE. That's 2003 to 2018, so 16 years of data in there. And so that was 2 kilometers hourly, and we were able to upsample that to 30 meters so we wouldn't have any seam lines, and basically took those and converted them into what we're calling a WTP, a weather type probability. So 216 weather types, and then 216 weather type probability rasters at 30 meters, and then 216 FlamMap outputs at 30 meters, and then we weight them all together. And what you get is what I'm going to show you right now. This is actually flame length here. Flame length, and then here's fire intensity. Yeah, so there's flame length. But we can do all kinds of other things other than just like an average flame length. So this is what's the likelihood of exceeding manual control. So how often those WTPs, what's the sum of the WTPs for all the weather types that exceeded 4-foot flames at the head of the fire. So that's what this looks like. 8-foot flames for exceeding mechanical control. So you're less often going to exceed mechanical control. And then less often will you have it be at extreme fire behavior, which is 11 feet. So we just read the hauling chart, 4, 8, and 11 feet. So you don't have to just use averages. You can do other stuff. And in fact, I'm not showing them here, but what we can also do is have fire type probabilities. So you can say, well, what's the probability of having a mid-grade passive crown fire or worse, or just passive or active? You can convert that into a probability instead of just a yes or no thing. More fire intensity, so that conditional risk to potential structures measure, that's from the Wildfire Risk to Communities Project, WRC. That's really, it's a flame length converted into like a 25 to 100 scale, but then this legend, it looks like it's just on percentiles anyway. So that's really just a flame length thing. And then we did some other measures of integrated hazard. So risk to potential structures is the last one, CRPS times the burn probability. And then this legend here is just on some percentiles. That's one integrated hazard. Another one is the Wildfire Hazard Potential, or WHP, that Greg Dillon and Jim Anakis developed there here in Missoula. And so we used their model, but applied the data, the fine scale data that we produced for this project for that. And then Suppression Difficulty Index. Kit O'Connor and others here in Missoula have been working on making the Suppression Difficulty Index. This actually, well, yeah, this one here is the 2020 model, version 2020 of SDI on the 2020 data set. And then this next map is the same data, but it's a slightly different model of STI. They call it the 2021 STI model. And actually now there's a different legend to go with this. So, but we can do those. We did them both. So those are some integrated measures. We also did some burn probability modeling, sorry, Ember modeling, more interesting. Ember modeling that is sensitive to producing embers at certain locations and as a function of fuel weather and topography and the fire behavior. So you launch embers as a function of fire behavior, including from, we built our model to launch embers even from shrub and even grass fuels. Not as many from grass fuels as anything else, but it's also, we also made it not zero, but chaparral in our model can launch embers. And then we just used Albini's models in tabular form to look at distances, maximum distances, and using Mark's negative exponential to look at, well, how far do most embers go relative to their maximum? And then we did a 45-degree fan from the originating cell. Here's a little close-up view of that. So this is just for source cells that are, I think, 5 kilometers apart. And the max ember travel distance that we have here is about 1,500 meters. The reason these are not all uniform is that they're sensitive to the climatology at that source cell. And so at this source cell, the climatology there was launching embers to the northeast. Most of these were doing that, but yeah, it looks like most of them were doing that, but not all uniformly. So it was using all the information that we had about the fuel and the climatology. And then, yeah, we've been talking with Ben Gannon at the CFRI in Colorado about being able to do ember load, finding the source locations of ember load to buildings. He does it in a very nice vector world, and we think we can do that in our raster world as well. So that's the generalities. Ember, here's a map of the ember production. It's really, you know, it follows everything else, right? The higher the intensities, you usually get higher intensities from either being in heavy shrub fields or in crowning conifer forests. So here's ember production on a relative scale, and then ember load. So ember production is where they come from, the sources. Ember load is where they land. And this has a lot in it about directions and distances and everything else, but it really is just, it looks like just a simple smoothed version of it. It's just not that simple. But the number of embers in theory is identical between the production and the load. They just move in different places, and I'll be able to show you in a little bit how that worked. And then this is a little add-on that we did, so that risk to potential structures from the Wildfire Risk to Communities project is we added another one. So structure exposure score is got probability, flame length, and ember load. So we added the ember load factor to that, and ended up dividing California into 10 classes. Class 1 is that same 10% that doesn't burn, and not only doesn't burn, but it's also not close enough to burnable fuel to get ember load or to get structure to structure ignition, that kind of stuff. And then this is the graph there is showing the fraction of the landscape in these different classes, and there's a tiny bit of class 10. I'm actually not sure where it is on there. That is the land area distribution. This is the sum of an estimate of population or housing unit density, of a number of housing units within each of those. So again, class 1 is essentially not exposed to fire. Our estimate is that 58% of the people or the housing units are in that not exposed to fire. Class 2 is really not very exposed to fire at all, but not zero. And there have been a lot of losses in class 2. That's another 18%. And then we did find a very small number of housing unit density pixels in class 10, but actually we think that those are false positives from the Microsoft building footprint data set that we used to build that. So those false positives are a really big problem, and they're out there in the middle of nowhere sometimes. So we might have to go work backwards from these highest risk pixels and find out which home site in California is the most exposed to fire. Okay, and then some next steps on this project. We can actually do a preview today of the risk to California communities. So basically taking the risk to potential structures and the housing unit density for California and summarizing them for named communities, about 1,700 named communities across California. So I've got that to show in a few minutes. We're already underway on updating everything that you've seen here to reflect the 2020 fire season in the fuelscape. So we've finished updating the fuelscape, or a couple little details to track down. And then we'd have to run through the fire modeling all over again. So that's underway. And then we're under contract with California BLM to do a risk to homes, infrastructure, and surface drinking water, critical infrastructure through Homeland Security. So kind of a pilot risk assessment across the state. It doesn't include any of the really challenging, more resource-based, like timber and wildlife habitat. So those could come at a later date. And then that ad hoc group that I mentioned, we're looking at future work. So another update in 2022 and recalibration. So to revisit the rules that we reviewed a little over a year ago and see if we still like them. Doing risk to additional resources and assets, building a treated fuelscape. So that is where you build a fuelscape that is where you hypothetically treat everything you can, and then you can make difference rasters then, like, well, what if we treated here? What if we treated there? And that could help you really look for opportunities that way. And then some of the really interesting opportunities is to build historical fuelscapes and then historical hazard through time, and with one methodology, right? So we're going to go 2020 to 2021, and that should be pretty interesting to see how well, obviously the 2020 fire season reduced hazard where it burned, but other old fires will be increasing. And so we can go backwards in time and near future fuelscapes and hazard. We can go forward a little bit by looking at two things. Looking at one is the trend in historical occurrence and assume that might continue. And also to look at how the fuelscape past fires will heal over the next 5 to 10 years, and to see what the next 5 to 10 years could look like in terms of burn probability. So that's what's coming up in some of the next steps. And I think what we should do now is I'm going to show you where you can actually browse online, not all of the data sets that we produced for this project, but I think 4 or 5 of them. So let me see what is the best way. Are you guys seeing a web map now?
Yes.
Okay, great. Okay, so this is our burn probability map for the state of California. And we can put on, here's the 2020 fires, and you can sort of, we've already looked at this and flipping them back and forth in the PowerPoint, but just to see, convince yourself that, yeah, they did happen to occur in places that were high likelihood. And I'm just gonna zoom in now. One of the things that you can see is like all the splotchiness, right, of the BP is, what's that from? You guys all know, in general, those were past fires. And so I can turn on, we only went back in 2 5-year periods because that's how we do our fuelscape. So we're not going back to see when all the fires were. The darker ones are within the last 5 years, the lighter gray ones were 6 to 10 years. And so you can kind of see that it's being a little bit finicky right now, but how, yeah, past fires influence the contemporary fire season, right? And then turn those off. We have this kind of a handy feature where when you just single click anywhere on the map, it actually shows you where you are on our, this is actually our legend. This is the colors match. And that was where I clicked, was a 99th percentile of the state. The BP was 0.073. So it shows you the percentile here and the value. So that's the burn probability. And well, if I just click right over here, so that's 100th percentile, 12.7%. So yeah, that's right close to that, the maximum within the state, which interestingly is not in Southern California like it used to be. It used to be that the highest burn probabilities in the state were in Southern California. But when we accounted for the trends in Southern California were fairly flat, not increasing very much, but they increased a lot in Northern California. Let me come right here, and here's Suppression Difficulty Index. That's the 99, where I had clicked before, is a 99th percentile for SDI. Wildfire Hazard Potential. Again, the 99th percentile for that one. Damage potential. This is not one I've talked about yet, but damage potential is analogous to that CRPS, conditional risk potential structures, but it also has Ember load in it. And I think the best way to show how that works is to zoom in to this spot. Actually, yeah, there's a lot to talk about in here. So turning on my reference layers, that was, I don't know the name of that fire, you guys know, but there was a wildfire here between 2015 and 2019. And so that is why there is this, there's a reduction in our damage potential. If I click inside there, that's the 17th percentile. Click out here, that's the 99th percentile. I don't know what these were before the fire occurred. That's what we'll have to get when we do our historical work, right? But one of the things that you can see is that there is a shadow of increased damage potential coming from the northeast to the southwest, and there isn't a shadow down here going the other direction. And this is the effect of Ember load. Our model right now for damage potential is giving roughly equal weight to Ember load and to fire intensity. And so that's what you're seeing here, is that this area, and in this area there therefore was a northeast to southwest Ember carrying wind propensity, and that's why you see that shadow there. And if I come out here, you can also see that the embers are traveling into the lake, whereas so WHP it doesn't have that, right? So WHP and suppression difficulty, they stop at the lakeshore, but damage potential. So if you have a boat, there's some potential for getting embers out there. It's still not gonna be very high, right? Yeah, that's the 9th percentile in the state, because it's not making any intensity. So it can't give you intensity, but you can still get some ember load on it. And then the last one is that structure exposure score. And now I can show you, we have housing unit density as a reference layer that you can turn on. And this is a layer that we built for the WRC project, the Wildfire Risk to Communities. So the housing unit density, it's a combination of Microsoft building footprints and census data. So we took census data resolved down to the block level, and then moved the population count to where the buildings were in that block, and then did some smoothing. And it works pretty well. It fails occasionally, and we got to do some workarounds, but it does work pretty well. So I think this is a cool map that you can now drive around and look at, well, any one of these burn probability or structure exposure, suppression difficulty, and you can look at them with housing unit density and just see where they interact. And then maybe when we get to the Q&A session, we can come back to the map and drive around. Well, actually, and you guys have noticed probably right now already, right? So not the URL, but the domain name is wildfirehazard.com. And any of you who want to stop listening to me can go to wildfirehazard.com and eventually find your way to these maps and browse this yourself. Maybe don't do that just yet, but we can do that. We can do that in the Q&A afterwards. And then the structure exposure score not only shows you the same percentile on the value, but it also on like a hauling chart for its damage potential and burn probability to show you why you got into that class, and which one of those was more dominant or less dominant. So it's just it's an art project of ours at Pyrologix. We did not build this for anybody for any particular reason. We kind of built it for ourselves, but I think that other people will find it kind of interesting. And then maybe, I think I do have time before we take questions to look at our wildfire risk to communities summaries across the state. And hopefully that is working. A nice black and white spreadsheet, not very pretty. But what this is, let me see how many communities. 1,513, I said 1,700 earlier, so it's a little over 1,500. These are either incorporated places or census designated places, which the census called, both of those together are called populated places. And then Alan Ager and his crew devised a way of taking, those are sometimes small polygons, like especially if it were a city, of expanding them by so the area around a CDP, whichever one it's closest to by drive time, it gets added to that. And then they put a limit of 45 minutes on that. And I think probably 99% of Californians live within 45 minutes of one of these populated places. So I haven't looked too closely to see how these results differ from like the WRC project, and I'm realizing now what I should be able to do. Yeah, I should have practiced this before. Turn that, well, I should just turn that back on. No, turn that back on too. Is to see, these are sorted now from the most at risk on average. So the fact that it's a small number of population and housing unit count, this is not a penalty. So of the houses that are there, what is their average RPS, risk to potential structures? And I don't have RPS by itself on the map, but we do have structure exposure score. So the highest was Douglas City, which is way up here. I'm gonna I'm going to lose it now. Where, yeah, you guys can't help me. I can't hear you, but it's in this area somewhere near Hayfork. Yeah, it's in that area. So this is a lot different, I think, than it used to be. I think that almost all of our risk was in Southern California, which it is, right? So Pine Valley, Campo, Descanso, Anza, Green Valley, Castaic, these are all in Southern California. And that's where we have always kind of traditionally thought of where the highest risk to houses is in California. And then we come back up to Tehama County, Pesquenta. And then they kind of get mixed around. So Hayfork, which is near Douglas City on the Trinity County, they get kind of mixed around after that. Most of these communities are in Southern California, but a few are in Del Norte and Trinity County, and then eventually Plumas shows up, and the Sierra. Now, one thing too, I need to point out, I'm down here to I guess that's the 29th community by ranking, but if I over here and look, that's still the 99th percentile by exposed housing units, because these are such, on average, low exposed population places, that there's not many people who are exposed to fire in these communities. And that's how we calculated these percentiles. So it's basically only 1% of the housing units are on average in places that are worse than here and above. You're much further down that list when you look at it in terms of percentiles by community. And we also did this by county and county subdivision. We did it by zip code. We can do it by anything that anybody needs, but that's how we did these non-overlapping polygons across the state. So I see, wow, 17 questions, probably telling me they can't hear me. Hopefully not. But I think, Crystal, I'll turn it back to you to manage a couple of questions.
Okay, thank you so much, Joe. So again, folks, we will have just a few minutes here for questions. And then, of course, as usual, we have our hour-long discussion from 4 to 5 Pacific time with Joe. And the link for that, this is a separate Zoom where you can actually interact with him. And the link is now in the chat. It was also in the email you received. So if you're not able to get your question answered right now, I hope that you'll bump over to the Zoom and join us. So lots of great questions. And let's see, let's just kind of go down through the list here. So Jonathan Pangburn asks, does your fuelscape data account for discrepancies in LANDFIRE data not aligning, right? So things that we know are problematic in the LANDFIRE data, like EVT and fuel models not lining up and things like that.
Well, the short answer is yes, because what we did is we went back to the rules that LANDFIRE used, which uses EVT and existing vegetation cover and existing vegetation height and sometimes other things. And we reviewed those rules, both ourselves and with 2 different groups of experts across the state. And if there was something that people didn't like or did not align, we corrected it. And that's not to say that we got every single one of those corrected. But usually if there's a problem with EVT and fuel model not aligning, it's because of a rule, and that's how we calibrated the fuelscape.
And then Jonathan's follow-up to that was, how did you determine the group areas for your FSim analysis, given that some of those groups are really different from each other?
Yeah, and I think we had actually had 17 individual fire occurrence areas across the state that we grouped into those 3 different pyrome groups. And the reason we had to do a big group was to make sure we got enough fire occurrence data. So since we did this work here, Chris Moran, who you can ask, he'll be in the chat after this, he recently ran an analysis across the country that did not require, it was a moving window. It was 750,000 overlapping regions. And so if there is a fine scale, if there's a spatial pattern, we will now see it.
Several people asked, and I think Dave Sapsis also put a note in the chat about this to try and answer, but people want to know where the 10% probability was.
Yeah.
And I think Dave put in that it was somewhere in Tehama County. I'm looking for
yeah,
this.
I think
Northwest Tehama.
So if you can still see my, if I'm still sharing my screen.
Yes.
Yeah, so it's this area right here. So where I just clicked, it's the 100th percentile. It's a 12.6%. And so that very darkest red that you can see here, that's that's that highest burn probability. And then here's the August complex that I admit to getting lucky that we did burn some of that. But in general, our modeling, so in California, this, and I get it that the MODOC is probably bringing the average down a little bit, but there were the strongest increases over time in this area of California. One of the few places that has a stronger trend than here nationwide is the Pacific Northwest, west of the Cascades. Is an even stronger upward trend here, but there's a lot more fire here to begin with, so it's way more consequential here.
Okay. And then, boy, Michael Warr, I hope you're going to join us in the discussion, because I think your question deserves a much longer discussion period, so I'll skip over that. Carrie Metlin has a question. Hey, Carrie, have you begun to use any of the residential fuel models, or do these runs treat developed spaces as unburnable?
Well, both. we have, so what we've been doing, we've been trying a number of things with different projects across the country. And one of the things that we did was developed a fuel complex to represent certain types of subdivisions or whatever. And that fuel complex, I won't tell you what it is because it won't make any sense to you. It's a certain fuel, it's a certain standard fire behavior fuel model with a certain base height and a certain bulk density and a certain canopy cover that in reality, there's no basis in reality for it. But what it does do is we tried to get relatively low spread under mild and moderate conditions, and then finally decent spread when you get wind speeds up around 20 to 25 miles per hour and above. And then we only apply that under the driest conditions. And so it's a lot of art to do that in here. We're not, by any stretch do we think that we're done messing with that. But then what we did in the end actually is a lot like what we did in the WRC project, is clip back to the non-burnable and then oozed probability, in this case 900 meters, which is what Mike Caggiano found in a paper that he just had come out a couple of weeks ago, or maybe a month or two ago, about that. He said he wasn't really seeing losses much further than that from burnable fuels.
Okay, so it is 4 o'clock, folks, and that means that we need to wrap up the general webinar. So if you would all please join me in thanking Dr. Joe Scott. You're not a doctor. I'm sorry. I always just, you have published far more, so much over the years. One of these days we need to make sure you get an honorary doctorate. Maybe we should work on that here in the UC system. Anyway, have certainly contributed substantially to the science in this arena over the years. So thank you all for joining us. Again, this is our last seminar of the semester, or of the year, actually, the academic year. The link to continue this discussion with Joe is in the chat. So I would ask everyone to go ahead and click on that link and you can bump over to continue this discussion. I'm sure it'll be a lively one today. And we hope to see all of you again in the fall as we kick off the next academic year seminar series. Thank you very much. Okay, and I'm going to stop the recording.